For our next lesson, we're going to look at applications of matrices. So basically what this means is using a matrix to solve a word problem. So first of all, we need to understand how to use matrices to solve systems. So we're going to talk about solving systems with matrices. So for example, if you had the system 2x minus 3y equals 4 and x plus 5y equals 2. We know our normal ways that we could solve that as a system, but using the idea in our previous lesson, if I let matrix A be the coefficients 2, -3, 1, and 5, and let the x vector matrix be x, y, and then the B vector matrix be the constants 4 and 2. Since we know A times the x vector is our coefficient matrix times our variable matrix, by multiplication, if I took the first row times the first column, I would get 2x minus 3y, and then second row times the first column, x plus 5y. And we know what the B vector is, 4, 2. We have our matrix equation. That matrix equation being A times x equals B. So any system can be written in that form. Going from there, if the inverse of A exists, then we can solve for the x vector, which would tell us what our two variables are, by multiplying A inverse times the B vector. So why is that true? We're going to do a quick little proof here of why that works. If we assume the A inverse exists and that we're working with the matrix equation A times x equals B, then by multiplication properties, we can multiply A inverse times both sides of this equation. We can use the commutative property of multiplication, since we learned that that is true for matrices. And A inverse times A gives us the identity matrix. And the identity matrix times any matrix just gives you the matrix by itself. So then it is true that the x vector can be solved for by multiplying the inverse of A times the B vector. So remember, matrix A must be square for a unique system to exist. Sorry, unique solution. All right, so moving into our first example. Our system here. This is our system. So the first thing we do is write the system as a matrix equation. So we get our square matrix of coefficients. Our letters will be X, Y, and Z. So our second equation doesn't have a Z, so we put a 0 placeholder. So that coefficient matrix times the column matrix of our variables will be equal to the column matrix of our constants. Second step, we're going to find the inverse of A using a calculator. So you can create the double width matrix with the identity matrix and do reduced row echelon form, or you can use the A inverse button. Whichever way you choose, make sure that you are able to generate this inverse. So we have 1.5, 0.5, and negative 1.5 as our first row. Negative 1, 0, 1 is the second row. 0.5, negative 0.5, and 0.5 as the third row. And then using our matrix equation for the third step, we're going to find the value of A inverse times B. So inverse matrix times the column matrix of our coefficients 2, 5, and negative 1. You can put both of those into the calculator, say as A and B, or you can use the A inverse button on your calculator times the B matrix, and you should get 7, negative 3, and negative 2, which corresponds to our variable matrix. So the values of X, Y, and Z. So our solution would be 7, negative 3, and negative 2 as our fourth and final step. Okay, example number 2. We're going to use the inverse of the coefficient matrix to solve. So rather than giving it to us as equations, that statement is said first, then the system is given. So just making sure your vocabulary is clear. This is our system. We don't have any matrices yet. We're instructed to use the inverse of the coefficient matrix. That means we need to define our coefficient matrix. We only have 2 variables, so 1, 1.5, 2, and 3. When you put this into your calculator to find A inverse, this one's going to give you an error. And remember from our last lesson, that means we have a singular matrix. So sometimes that means there's no solution. Sometimes it means there are multiple solutions. So we revert to our backup plan. Our backup plan is to create the double column matrix with the identity matrix, do reduced row echelon form, and that gives us 1, 1.5, and 0 on the bottoms. And this is just giving us a way to verify that this is not the identity matrix. So now we can definitively say that this has no solution because we were not able to find the inverse of our coefficient matrix. So now I'm moving into the application ideas. Most of our problems are going to deal with input and output analysis, building into the business idea. In the business world, it's all about analyzing your input and your output. So for our word problems, we are concerned with the production and flow of goods from the various different sectors in an economy. Each sector requires input from other sectors and sometimes from itself to produce its output. So if an economy has n sectors, then the inputs are summarized into an n by n matrix called the input-output matrix. So when we work our application problems, we're actually going to be creating the input-output matrix from the given scenario. So number one says, suppose a simplified economy involves just three sectors: agriculture, manufacturing, and transportation, all in appropriate units. The production of 1 unit of agriculture requires half a unit of manufacturing and a quarter of a unit of transportation. Production of 1 unit of manufacturing requires 1/4 of a unit of agriculture and 1/4 unit of transportation. And the production of 1 unit of transportation requires 1/3 unit of agriculture and 1/4 unit of manufacturing. So step one, part A, asks us to write the input-output matrix of this economy. So for this particular economy, there are three sectors. So we know that will create a 3x3 matrix. The 3 rows and the 3 columns will be labeled as the 3 sectors. So I'm going to choose the top going across the rows, or sorry, the columns of our matrix to be the output of the agriculture. And then the next thing that's listed is manufacturing, and then transportation. And then working our way down the rows is going to be our input, and I'm going to put them in the same order: agriculture, manufacturing, and transportation. So to output a unit of agriculture, the word problem says that we are required 1/2 a unit of manufacturing. So under the output of agriculture, I go to manufacturing and put a 1/2. And 1/4 of a unit of transportation. There is no mention of agriculture needing itself, so that gets a 0. Manufacturing requires 1/4 of a unit of agriculture and 1/4 a unit of transportation. It does not rely on itself. And then transportation relies on 1/3 a unit of agriculture, 1/4 unit of manufacturing, and no dependency on itself. So A is going to represent our input-output matrix, and it's going to be exactly what I wrote down right there. It's a good idea to label your rows and columns in the words of the problems like I did, so that when you get to your solution, you can refer back to that and see how you organized your information. Okay, part B says, suppose the economy produces 60 units of agriculture, 50 units of manufacturing, and 48 units of transportation. That is what our product should be equal to. So now we're making what's called the production matrix. that is a column vector of our constants, the output. So those would be like our variables. Okay, part C says how much from each sector is used up in the production process. So when we multiply our A vector times our X vector, that gives how much from each sector is used. So we're going to multiply A times X. So copying down my A matrix. Multiplying that by production matrix. You can use the calculator to do that, or you can multiply manually. The result you should get is 29, 42, 28. What that translates to is that 29 units of agriculture were used, 42 units of manufacturing, and 28 units of transportation. Okay, and then part D asks us to find the matrix D, which is X minus A times X. So X is the production matrix we created in part B. A times X is the solution we found in part C. So to do part D, find the D vector is the X minus A times X. Our production matrix was 60, 52, 48. Subtract from that our solution, 29, 42, 28. We use corresponding elements and do the subtraction. We get 31, 10, and 20. So that's telling us the amount of each sector that is not used in the production process. And that just gives you a chance to reflect on what was not used and what you still have available. So hence that amount that's left over, it is available to groups outside the production process. We call the D matrix the demand matrix. And when this is used in practice, the input-output matrix and the demand matrix are known. However, the production matrix is unknown and needs to be found to ensure demand is met. Okay, so let's think about the equation we used to find the demand matrix. We said the demand matrix is our X matrix minus the product of A and X. So I can throw an identity matrix in here beside the X matrix. I didn't change anything. That's just like putting a 1 in front of a variable. And I do that so that I can factor out the X matrix. So if we assume I minus A has an inverse, we can find our production matrix by multiplying that inverse times the demand matrix. So we're going to put that into practice on our next problem. An economy depends on two basic products, wheat and oil. To produce 1 metric ton of wheat requires 0.25 metric tons of wheat and 0.33 metric tons of oil. The production of 1 metric ton of oil consumes 0.08 metric tons of wheat and 0.11 metric tons of oil. Find the production that will satisfy a demand of 500 metric tons of wheat and 1,000 metric tons of oil. So we're going to again begin with our input-output matrix. The two things we are discussing in this problem are wheat and oil. So using matching orders, label your rows and columns. And remember, the top refers to the output. So the output of 1 metric ton of wheat requires 0.25 metric tons of wheat and 0.33 metric tons of oil. And for oil, we need 0.08 and 0.11. That is our A matrix. We are given the demand. So our demand matrix is 500 metric tons of wheat and 1,000 metric tons of oil. Okay, looking at what here is at the top of the screen, what we're looking for is the production matrix. So we need to calculate I minus A, I being the identity matrix, so 1 minus 0.25 is 0.75, 0 minus 0.08, negative 0.08, 0 minus 0.33, negative 0.33, and 1 minus 0.11 is 0.89. Now we need I minus A inverse. You can use your calculator to verify. This gives you some very odd decimal points, and it will not convert to fractions. So I'm just going to write all of the decimal points I could see on my calculator. And then our production matrix is equal to that inverse times our demand matrix. So that I minus A inverse matrix times the demand of 500 and 1,000. If you multiply those in your calculator, you will get 818.91 and 1427.23. So to interpret that means to satisfy demand, the economy should produce 819 tons of wheat and 1,427 tons of oil. And the last little concept for this lesson, it's kind of a fun application of this called code theory. For code theory, we will use the following mapping that I'm about to give you to convert letters to numbers which we could then use matrices to send secret messages. So our mapping, I'm going to write parts of the alphabet here, and I'm going to skip and pick back up with W, X, Y, Z. So we're going to map the letter A to the number 1, B is 2, C is 3, D is 4, and so on. So that means Z would be 26, Y would be 25, X would be 24, and W would be 23. And we'll have to interpolate between those two for any other values we need. And then we're also going to put one for spaces. So when we have a phrase, we usually have several words. So we'll call the number 27 our space code value. So for this example, we want to encode, that means put something into code, the message, math is fun. We're obviously going to ignore case. So when we do this, we're going to work in groups of 3. So I'm going to first take MAT. M would be the number 13, A is 1, and T is 20. After T is H, then a space and the letter I. So H is 8, space is 27, I is 9. After the I is an S, and then space, and then F. So 19, 27, and 6. After F is U, N, and I've run out of letters. So again, I'm just going to put an excess space at the end because I need some kind of placeholder. And these are the values that go along with that last piece. So if you're looking at that code and the numbers, that's pretty easy code to crack. So to make a stronger code, we can make what's called a key. The key needs to be a 3x3 matrix, and it has to be invertible. Means it has to have an inverse. Okay, so I'm going to call this matrix M. It's going to be my key. My key is 1, 3, 3 for the first row, 1, 4, 3, 1, 3, 4. And just as a note, to decode the person on the receiving end, needs to be given the inverse of M. They're going to have to use the inverse of our key in order to crack the code. So now we're going to encode these matrices that we came up with up here, which clearly just map the letters to their numerical order in the alphabet. So now to encode, the first matrix, we're going to take our M matrix and multiply it by our first column matrix, which was 13, 1, and 20. If you multiply those, you'll get 76, 77, 96. Second matrix from our original encoding. Take my key, multiply it by the matrix 8, 27, and 9 to get 116, 143, and 125. Third small matrix. 19, 27, and 6 multiplied by my key is 118, 145, and 124. And then the last one, the original coded matrix was 21, 14, 27 multiplied by the key 144, 158, and 171. So our message in matrix form will be our encoded 76, 77, 96, 116, 143, 125, 118, 145, 124, and 144, 158, and 171. Now there's no obvious pattern to the way that we labeled our numbers and with our letters. So if you're on the receiving end of this, decoding takes a little bit more work. So rather than use that example, I'm going to start with a fresh example. We're going to decode the message 57, 129, 37, 79, where our M matrix is 1327. So that process starts with getting the inverse of M. Sorry, that is a 2 by 2 matrix. It's supposed to be a square. 1, 3, 2, 7 is M. Its inverse is 7, -3, -2, and 1. And then to decode, you multiply the inverse matrix by each of the 2 coded matrices. So the first one gives us 12 and 15, referring back to our original code, that is L and O. And then same inverse matrix times our other coded message, coded piece, gives us 22 and 5, which corresponds to V and E. So love is the encoded message. So our final problem from the word problem pages is to decode this message. It didn't exactly print in the proper form, so let me show you what it's supposed to look like. The message is supposed to be 3 column matrices like we had on the other problem. So the matrices are correct. They're just written as row matrices rather than column. And you get the picture. And then the key should be the square matrix. That's a 3 by 3. 1, 2, 3, 0, 1, 4, 5, 6, 0. So to decode this big long message, just like the other one, we start with finding the inverse of the key. Using your calculator, the inverse of the key is -24. 18, 5, 20, -15, -4, and -5, 4, 1. And then you begin the process of decoding. To decode, you take the inverse of the key and multiply it by each of the column matrices of the message. So this first one is the letters H, O, O. And if you go all the way through to the end, like the completely decoded message is hooray for the weekend. And that finishes out this lesson. Sorry, I just realized I made a mistake back here. This should be multiplied by the column matrix. The product of those two matrices is 8, 15, 15, which decodes to HOO. So notice the strength of encoding the message. This column does not have two of the same numbers here, but after decoding using the key, we do end up with the same two letters. So it's a very strong way to code a message.